Bismillahirrahmanirrahim. Hello everyone. I hope you are all doing well. I welcome you all to the class of real analysis. Here we are using the book Introduction to Real Analysis by Robert G. Bartle. In today's lecture, we will discuss three types of functions: uh, surjective function, injective, and bijective functions. We will discuss how to check if a function is given graphically is a surjective function, injective, or bijective. Further, we will discuss the mathematical criteria to check all types of these three functions. And in the last segment of the lecture, we will discuss two important problems, question number 16 and 17, available in exercise 1.1. You will see question number 16 needs for correction. There is some mistakes available in question number 16 that we will discuss, inshallah. So let us start the three types of the function. Suppose this is definition 1.1.9 available in your textbook. I am using here the latest edition, that is the 4th edition. Let f is a function from a to b, then f is called injective function or also called 1 function if whenever x1 is not equal to x2, mean to say when your pre-images, these values of x are called pre-images. When your pre-images are different, then if your images are also different, then f is called injective function or 1 function. If f is injective function, we also say that f is an injection. The function f is called surjective function or also called map a onto b if f of a is equal to b. In other words, we can say that if the range of f, rf mean range of f, if the range of f is equal to the second set b, then f is called surjective function. If f is surjective function, we also called f is a surjection. C. If f is both injective and surjective, then f is called bijective function. If f is bijective function, we say also f is a bijection. So these are the basic definitions of these three types of functions. Next we discuss the mathematical criteria to prove injection and surjection of f. To prove that a function f is injective, we must establish that we will take any 2 points x1 and x2 from the domain, and we will take f of x1 equal to f of x2. If f of x1 is equal to f of x2 implies x1 is equal to x1 is equal to x2, then we say that f is an injective function. You can prove the injection of a function by two ways. One of the ways, if you take x1 not equal to x2, then you need to prove f of x1 is not equal to f of x2. The other criteria is this: if you take images are equal, then you need to prove their pre-images are also equal. We discuss a simple example of identity function here. Suppose f of x is equal to x. x1 and x2 are the two elements in the domain of f. Then if you calculate f of x1, your f of x1 is equal to x1. If you calculate f of x2, then this is simply x2. Now if you use this criteria, take f of x1 is equal to f of x2. Here f of x1 is equal to x1 and f of x2 is equal to x2. This shows that when you take f of x1 is equal to f of x2, this implies x1 is equal to x2. That is, for the same images, the pre-images are same. This shows that your function, this function, identity function, is an injective function. To prove the surjection, We need to show that for any b belong to b, there exists at least one x belong to a such that f of x is equal to b. This equation shows that uh, element every element in b is an image of some element in a. We can discuss this definition grammatically as suppose this is your set A, this is your set B, and this is function f from that maps every element of A to B. Suppose there is a element here x1 in A. When you apply x1 f on x1, it map x1 to f of x1, and f of x1 is an element of B. Again, there is an element x2. If you apply f on x2, there is a corresponding element f of x2. If for every element of A you find an element in B, then in this case f is surjection. But if on the other hand there is an element x1 here, x2 here, and there are here three elements f of x1, f of x2, and f of x3. x1 is related to f of x1, x2 is related to f of x2, and f of x3. For this element there is a no pre-images in A. Then in this case we cannot say that f is a surjection from A to B, because there is a here extra element f of x3 in B which has a no pre-image in A. So f is called surjection if for each element of B, if for each element of set B, there is an element available in A. So next we discuss the graphical criteria to represent three types of functions. This graphical criteria depend on horizontal line test. To check whether a function is a surjective function or injective function or bijective function, we use horizontal line test. A function f is called surjective function if and only if for every horizontal line y is equal to b with b belong to b intersects its graph at least one point. At least one point mean every horizontal line cuts the graph. At least one point mean one or more than one, greater than or equal to 1. F is called injective function if every horizontal line cuts its graph at most one point. At most one point mean one or less. One or less mean exactly at one point or at none of the point. A function f is called bijective function if and only if every horizontal line intersects its graph at exactly one point. Exactly one point. So in case of surjection, horizontal line will cut the graph at least one point, greater than or equal 1. In case of injection, your horizontal line should cut the graph at most one point. And in case of bijectiveness, your horizontal line should cut the graph exactly at one point. We discussed all of these three types by using these graph. I have considered example f of x is equal to x square, that is actually a parabola. Domain is set of real number r and the range is non-negative real number. You know, when you put any real number, your answer will be greater than or equal to 0. So the range of the function is non-negative real numbers. Then f is clearly surjective function. We can check it graphically. For example, consider the horizontal line y is equal to 9. Then it intersects the graph at 2 points, 3,9 and minus 3,9. Similarly, each horizontal line in the range of f cuts the parabola at 2 points except one horizontal line y is equal to 0, that is actually x-axis, cuts the graph of parabola only at one point. This shows that in case of surjection, the horizontal line must cut the graph at one or more points. This is the graph of the parabola f of x is equal to x square. You can see that this blue horizontal line, that is actually line y is equal to 9. This cuts the graph at 2 points, at 3 9 and minus 3 9. Again, this is x-axis, that is actually line y is equal to 0. This touches the graph at 1 point origin. So in this case, you can see that uh, every horizontal line either cuts the graph at 1 point or greater than or equal to 1. Mean to say, here this horizontal line cuts the graph at 2 points, and here this line touch exactly at 1 point. So this is the graph of surjective function. Again, I am taking here graph of absolute function f of x is equal to x absolute, whose domain is set of real number and range is non-negative real number. You can again observe that every horizontal line cuts the graph at least 1 point, like as similar as parabola. This black graph represents the graph of y is equal to x absolute. This blue line cuts the graph at 2 points, first here and second one is here, minus 3 comma 3. Again, this black line cuts the graph at 2 points again, and the x-axis touch the graph at exactly at 1 point. So this is the graph of this is graph also of surjective function. The third one, function f of x is equal to e raised to power x, absolute function. I am taking here the codomain. Actually, the domain of this function is positive real numbers. The range of this function is actually positive real number, but I am not here taking a positive real number. Here, codomain of function that I am using here is actually set of real number R. So this is not equal to the range of function here. The range of this function is positive real numbers. So here, that's why this function is not a surjective function, but it is clearly injective, because if you draw every horizontal line, you will see every horizontal line cuts the graph at most 1 point. At most 1 point. Like as this horizontal line cuts the graph at exactly this point. This black line again cuts the graph at exactly this point. X-axis, that is actually asymptote of this graph, never cuts the graph, never touch the graph at any point. Again, this green line, that is actually the part of a domain. Your domain is set of real number R. So this line, that is y is equal to minus 1, that is actually part of the domain, cuts the does not cut the graph at any points. So you can see that every horizontal line cuts the graph at most 1 point, either at 1 point or at no point. So this is the graph of injective function. The last one, consider the function f of x is equal to x cube. This is clearly a bijective function. We can observe that from its graph that every horizontal line cuts the graph exactly at 1 point. This green line cuts the graph at this point, exactly at 1 point. Again, the x-axis touch the graph or cross the graph at origin, and this blue line again cut the graph at exactly 1 point. So y is equal to x cube. This is the graph of y is equal to x cube. Is a graph of bijective functions. So this is the criteria to check whether the given graph is graph of injective function, surjective or bijective function. Next, we discuss an important example available in your textbook, example 1.1.10. uh, given set A is x belong to R except x is equal to 1. Mean to say your set x is a set, all set of real, all those real numbers which are not equal to 1, defined by the function 2x over x minus 1 for all x belong to A. We show that f is injective function. To show that f is injective function, we take 2 points x1 and x2 in A and assume that their images f of x1 and f of x2 are same. We will show that from this expression, when f of x1 is equal to f of x2, we show that f x1 is equal to x2 here. Your f of x1 is, by just putting here x is equal to x1 in your function, we find 2x1 is over x1 minus 1. Similarly, when you put here x is equal to x2, we have 2x2 over x2 minus 1. By cross multiplication we have, and firstly by cancelling 2 from both sides, and after cross multiplication we have x1 into x2 minus 1 equal to x2 into x1 minus 1. By multiply x1 inside the bracket, we have x1 into x2 minus x1 is equal to x2 into x1 minus x2. Subtracting x2 into x1 from both sides, and by cancelling minus from both sides, we have x1 is equal to x2. This shows that when we take f of x1 is equal to f of x2, then x1 is equal to x2. This shows that your function f is injective function. Next, we show that f is also surjective function. To show that f is a surjective function, we need to show for each y belong to range of f, there exists x belong to A such that y can be written as y is equal to f of x. So for this, firstly we find what is the range of the function. For this we determine range of f. We solve the equation y is equal to 2x over x minus 1 for x in term of y. To find range, we find the value of x from the given function. So from this expression, when you solve this equation for x in term of y, we find x is equal to y over y minus 2, which is meaningful for y not equal to 2. That is, this expression is not hold, does not hold for y is equal to 2. Thus the range of the function is all those real number except y not equal to 2. This shows that your function f is surjective function. How? You claim that your range, for any y belong to B, there exists x belong to A such that you can write y is equal to f of x. Suppose if you say for which x belong to A, there exists y is equal to 9. Suppose, mean to say you want to find what is the pre-images when image is 9. So you just put y is equal to 9 in the expression x is equal to y over y minus 2 here. We have y is equal to 9 minus 2 7. This shows that when x is 9 by 7. Now you have to see whether 9 over 7 belong to your domain or not. Your domain is all set of real numbers except x is equal to 1. This clearly shows that this number x is equal to 9 by 7 belong to A. So this shows you can find at least one x for given y belong to range. As our function is injective plus surjective, this shows that finally the function is bijective. Thus f is a bijection of A onto B. Next we discuss an important question, question number 16, that is actually needs correction. In the question, author claims that show that the function f defined by f of x is equal to x over square root x square plus 4, where x belong to R, is a bijection of R onto set open interval minus 1 to plus 1. So firstly, when we check this function for injection, This function is not an injective function. Next, let us check f for injection. We take any 2 points x1 and x2 from domain of the function, which is given here, set of real number r, and assume that f of x1 is equal to f of x2. What is f of x1 here? By just putting here x is equal to x1 on both sides, we have x1 over square root x1 square plus 4. Similarly, f of x2 is equal to x2 over square root x square plus 4. By squaring on both sides, we have this expression, and by cross multiplication, we have this equation. Multiply x1 square inside the bracket, we have x1 square, x2 square plus 4x1 square. Similarly, after multiply x2 square inside the bracket, we have this. By cancelling out x1 square into x2 square from both sides, and further by cancelling 4 from both sides, we have x1 square is equal to x2 square. By taking square root on both sides, we have two values of x1, which are x1 is equal to x2 and x1 is equal to minus x2. This shows that f of x is not injective function over R, because for injection, if we take f of x1 is equal to f of x2, this implies only x1 equal to x2. But here x1 is equal to minus x2 also. This shows that our function f of x is not injective over R. But if we restrict our domain over just non-negative real number, then f can be a injective function. So for injection, f should have domain x greater than or equal to 0. In this case, our function f will be an injective function. So this is the mistake in this question. Further, to check whether function f of x is a surjective over this open interval, we find the range of the function. For range of the function, we solve this expression for x. So by cross multiplication, we have y into square root x square plus 4 is equal to x. By squaring on both sides, we have this expression. By shifting this term, y square x square on the right side, we have x square into 1 minus y square is equal to 4y square. And from here, x square is equal to 4y square over 1 minus y square. Now, we need to find the range of the function. There is no need to taking square root on both sides like this. We find range by using this way, as on the left side x square, which is always a non-negative quantity. So as x square is a non-negative quantity, this implies the right side also greater than or equal to 0. So this is a p over q form. This is a p over q form which is greater than or equal to 0 here. This is possible in these cases. As you know, a fraction is non-negative if when the numerator is non-negative and the denominator is positive. Case number 1. So if when the numerator is for the numerator, what is the numerator? Numerator is a 4y square. So by taking 4y square greater than or equal to 0, this inequality hold for all real number. In other words, when you solve this inequality, this will become y square greater than or equal to 0, and which y satisfied this inequality. All the real numbers satisfied this inequality. So from here y belong to R. In this case, when denominator is positive, what is denominator? Denominator is 1 minus y square. When 1 minus y square is greater than 0, this implies 1 is greater than y square, or you can write from here y square less than 1. By taking square root on both sides, we have y square square root less than 1. As you can write y square square root of y square equal to y absolute. This implies y absolute is less than 1. Lastly, you can use here inequality y absolute less than a, where a is a positive real number, can be written as minus a less than y less than plus a. So from here you can write this inequality. Now from 1 and 2, the common values of y that satisfied both 1 and 2 are these these values, that is actually the open interval. So in case of surjective, your question is correct, but in case of injection, your domain is not correctly defined. Case number 2, in this case, P over Q. This is the P over Q form, and P over Q form is a non-negative. This is also possible when numerator is non-positive and denominator is negative. But this case is not possible because y square, that is the nominator, that is 4y square, cannot less than or equal to 0 for any value of y. So hence f of x is a surjective in case when y belong to the open interval -1 to +1. Finally, if you want to correct this question, the function f of x is bijective, we should restrict our domain to 0 to infinity and range to 0 to 1. Why we are not taking here the range -1 less than y less than +1? In case of bijection, when you restrict your domain 0 less than equal to x less than positive infinity, then in this case your range should also be restricted, that is 0 less than equal to y less than 1. You can verify this range as when x approaches to 0, then your y that is y is equal to x square over square root x square plus 1 approaches to 0. And in case when your domain x approaches to infinity, then your y approaches to 1 here. So for the bijection, values of x, that is domain, lies between 0 to infinity and your range lies this. Next, question number 17. Question number 17 is an interesting question which says that for all positive real number AB with A less than B, find an explicit bijection of A where A is an open interval on to B is also open interval. In other words, we need to find a bijection like this. We need a bijection. Explicit bijection mean we need a function f, or we need a mapping in which y is a dependent variable that depend on some variable x, but should be a bijection function that maps every elements of this open interval to this open interval. So one of the mapping, consider the mapping f from open interval AB to open interval 0, 1 such that f of x is equal to x minus a over b minus a. This is a linear mapping, linear function or linear mapping. This function is a bijective function. You can check that this function maps every elements of set A to set B. For example, when you put here x is equal to a here, what is f of a? F of a become a minus a over b minus a, that is equal to 0. That is the first point lies in this approaches to this interval. So you can check that this function maps every elements of set A to set B. Next, to check whether this function is a bijective or not. For this we find whether function is injective or not. Function is called injective when we take f of x1 is equal to f of x2. What is f of x1 here? By just putting x is equal to x1 here, we have x1 minus a over b minus a, and f of x2 is equal to x2 minus a over b minus a. By cancelling b minus a from both sides, we have x1 minus a is equal to x2 minus a. Adding a on both sides, we have x1 is equal to x2. This shows that whenever f of x1 is equal to f of x2, this implies x1 is equal to x2. Implies our function f is an injective function. To check the surjectivity, to check f of x is the surjectivity, firstly we find range of f. For this we solve this expression for x. From here, by multiply on both sides or by cross multiplication, b minus a into y is equal to x minus a. Adding a on both sides, we have x is equal to b minus a y plus a. Clearly, for any y belong to this. If you choose any y belong to this open interval, we can find an x belong to this interval from by using this range. This shows that f is a bijection of a onto b. So these are the two problems that we have fully discussed here. Inshallah, in the next lecture, we will discuss inverse function. If you find these lectures are helpful for you, kindly like, share, and subscribe my channel. Inshallah, see you in the next lecture. Take care. Allah Hafiz.